We are going to look at MOSFET circuits that we use in amplifiers. Last time we looked at MOSFET DC circuits that were just random MOSFET DC circuits. And I'm not going to show you every single MOSFET bias circuit that exists, because there has to be something left for you to figure out later. So I'm going to show you kind of the most common and why we do it the way we do it, and then you'll have problems on Friday to do that, gives you more practice at this. But when we use a transistor to amplify certain signals, we can use MOSFET, or we can use the other kind of transistor, which we haven't covered yet. Basically, it has to have DC voltages applied to make sure that all the junctions that need to be forward biased are forward biased, and the ones that need to be reverse biased are reverse biased, and they have to stay that way. So an AC signal, of course, goes positive and negative, and so we need to have enough DC so that the positive and negative fluctuation doesn't change the biasing in the circuit. So the DC circuit basically takes any kind of junctions that we need, and this is good for bipolar junction transistors as well as MOSFETs, and it creates a situation that it's a stable circuit, and then if you vary the voltage a little bit, it won't matter. So with MOSFETs, we have to have the proper gate to source voltage and drain to source voltages. The reason we need to have that is the input of the AC signal usually comes in at the gate, which means it's going to make VGS change a little bit, and it can't change it away from the situation in which the circuit is in the saturation mode. So it has to stay in saturation mode. The same with the drain to source voltage. There has to be enough voltage there, DC voltage, so that that's where the output is most often, not always, but most often. And we need to be able to have no changing of the situation, so we won't want to have the transistor go into a mode that we don't like. So if we look at a very, very simple DC circuit, and this is so simple it doesn't even count as a bias circuit, it's not particularly practical, but we can take this and we can actually make a load line just like we did with diodes. So we can look at the MOSFET curves, and we can actually plot that onto the curves. And then wherever the load line intersects with the curves, that's where it's operating at the time. We choose that operating point. It's not a random thing. We choose it so that the voltage at the output has the maximum up and down that it can go without pushing the transistor either into cutoff or into the triode region. So we want it to have as much room to move as possible. Let's say we plot the load line for that circuit. The highest VDS could ever be would be the applied voltage VDD. So that would be if we had a circuit in which VDS and VDD were equal, that would be the maximum it could be. So that's where the x-intercept of the line is. And then the y-intercept is just the maximum current we could have, which would be VDD over R, and that would be if VDS was 0. That is how we figure out where the load line goes. And we want the Q point to be somewhere in the middle. And then when we apply a small signal, basically the operating point moves up and down the load line, kind of along that line, but hopefully it doesn't ever reach either triode or cutoff. So if we move it up too far, you see it loses a lot of its swing with the triode region, and if it's down at the bottom, it loses a lot of its swing because it basically just hits 0. So in both of those cases with those Q points, you would end up with a signal at the output that was either chopped off at the top or chopped off at the bottom. That's what would basically happen if the Q point was in the wrong place. We can also look at the voltage transfer characteristics, and this is just plotting VDS and VGS together. And this is a different way of looking at where cutoff, saturation, and the triode region are. So it's pretty much, if you will never have to use that equation up there in red, that just tells you how that curve came to be. So it's not a random curve, it's actually a mathematical relationship. And we basically don't use that much. We just kind of look at it as an interaction between VGS and VDS. And again, if we want to choose the Q point, we want to choose it in a place where it's kind of in the middle. Usually, when we choose where the Q point's going to be, we either want to know what the gain of the circuit is, so how much is the signal going to be amplified, and that'll tell us how much room is needed at the output, and basically what the maximum peak-to-peak output voltage is. We don't usually worry about the input voltage because that's usually really, really tiny. The output voltage is obviously the bigger thing, so that's usually what we look for. And if we want to make the output swing as big as possible, we choose the Q point between VDD and the value of VDS that's right at the transition point. We go right in the middle there. And it doesn't look like it's in the middle, it really kind of is. But you notice that VDS is pretty much exactly halfway between VDD and the saturation point. And usually the voltage at the transition point is relatively small. So oftentimes VDS is about half what VDD is. Not always, but often it's about half, and that gives you pretty much the maximum amount of swing at the output that you can get. So you could, if you wanted to, apply two voltage sources, because that's what was used at this sort of conceptual DC bias circuit, but that's terribly inconvenient and not economical to use two voltage sources. It's really, not going to work. Usually you have one voltage source that's powering it as a DC source, so you want to have a system in which you don't need two, you just need one. So the standard method, this is not the only method or the only kind, but one of the most common methods is to use a voltage divider from the source voltage and have the half or the midpoint between two resistors be at the gate, and you create a voltage divider at the input. And then you can also actually add a source resistor. It just adds some stability to the circuit. Oftentimes with amplifier circuits, not always, but often, the source resistor is actually bypassed with a capacitor so that it looks like it's not there for the AC circuit, but it is there for the DC circuit, and you can do that. We'll talk about that next week, not this week. So this is kind of what the standard NMOS voltage divider bias circuit looks like. The analysis starts with the input side, and we need to know what the voltage at the gate is. And the nice thing is, because there is no current flowing into the gate, it's just a voltage divider, literally. It doesn't have any weird other things going on, and when we get to bipolar junction transistors, this will not be the case. And then you do have to take into account there is some current flowing into the transistor. But with MOSFETs, you don't have to worry about it. So in order to find the voltage at the gate, we just use voltage division, and we get 5 volts for this circuit. So the voltage at the gate is going to be 5 volts. Now it gets a little trickier, because the problem with MOSFETs, the thing that makes finding the voltage at the gate so easy, is also the difficulty with them, in that there's no interaction between the input and the output except for the equation relationship. So there's no value that goes from one side to the other, which in a bipolar junction transistor there is kind of an interaction. So you usually end up having to solve 2 equations and 2 unknowns, or use a quadratic or something weird to get the bias point. So we will start and see where we end up going. So at the output side, we're going to use KVL, and we're actually going to go around kind of this loop. And actually, we're going to start here. So we're actually going to go here, here, and here to get to 0. So we go around, we get 5 volts minus VGS minus IDRS equals 0. Good equation. We can turn that into a nice linear equation, and then what we can do is take VGS and put it in the ID equation. So we know what VGS is based on the drain current. So we just basically have to put that into the equation, and then we get something kind of, not nasty, but a little bit, because we're not going to directly be able to solve for ID. We're going to have to do some solving as far as finding the values algebraically, simultaneously equation-wise, which you do not have to do with the other kind of transistor. So we have this equation. ID is 5 times 10 to the minus 4, and I just kind of combined things up a little bit. I took Kn prime W over L and divided it by 2 because that's what was called for, and then combined the gate voltage and subtracted the 1 volt for the threshold voltage. So we get 4 times 6,000, or 6 times 10 to the 3 ID. And then we basically are just going to go through and move things around. So I'm going to take the 5 times 10 to the 4 and actually multiply both sides by its inverse. And the reason for this is just because algebraically it's easier to figure out if you do that. So if you take that leading value and make it into a large positive number, eventually you're just going to be able to subtract it from the other side. So that makes it a little easier. So we get 2 times 10 to the 3 ID equals 16 minus 4.8 times 10 to the 4 ID plus 3.6 times 10 to the 7 ID squared. And then we can actually move things around and get a quadratic equation for which you will have 2 solutions, always. However you want to solve the quadratic equation is fine. Most people now have calculators that will give you the answer, or in my case, I use MATLAB because sometimes I need to make 5 different versions of this, and so MATLAB is really easy. But whatever you want to end up doing. And we get 2 values. We get 2 different currents, and you'll always get 2 different values, and one of them will be right and one of them will not be. I will tell you that most of the time, like if we take the larger value, 0.89 milliamps, and we calculate what VS would be, because we can take RS times ID and do that, we get a value for VS that's greater than the gate voltage, and that won't work. So usually the smaller current is going to be the one that works, and the larger current is not going to be the one that works. I don't think I've ever actually come across a case when that wasn't true. So that's usually what ends up happening. So you get 2 values, but one of the values is going to be the smaller one, and usually the smaller one is the one you will use. Of course, as soon as I say that, there will be one that comes up that's not like that, but that like literally has never happened. So I can't.
The exam, can you please make sure it's still?
It has to be because of the way the math works. So it pretty much has to be. Like when I do MATLAB, a lot of times it gives me 2 values, and I just let it go with both the values, and it's always really obvious which one is right. So anyway, we can find now, since we know what ID is, we know it's 0.5 milliamps, which is the smaller value, and now we can find all the other node voltages and branch currents if we want. We can, we know we have 0.5 milliamps going through both resistors, so the source voltage is going to be 3 volts, and VGS is going to be 5 minus 3, which is 2 volts. And then we can find the drain voltage also, which is 10 minus IDRD, which is 7. And VDS is always going to be some kind of voltage. If it's in right on the edge of saturation, it's going to be really small, like 0.2 or 0.3, but it'll just go up from there. So it should be a value that is, while it may not be exactly half, you'll notice that VDS is a little less than half of the source voltage, and that's about what you expect to find. It might be a little bit bigger, but it might be a little smaller, but it'll be about that same. Yes?
So the only purpose of RG2 is just to make that a voltage divider?
Yes.
Okay.
If RG2 wasn't there, the voltage at the gate would be 10.
Yeah.
Because there's no current flowing, so there wouldn't be any current through the 10 milliamp, 10 mega ohm resistor. So, and we can actually even find the current going through each one of the gate resistors if we want. Usually those resistors are large, and the reason they are is because when you start inputting a signal into an amplifier, you want the input resistance to be as big as possible. You remember we kind of covered that a while back, but you want it to be really big, and while the input to the gate is infinite, those resistors are going to have some of an effect. So we just make them large, and that works just fine.
Another conceptual question.
Yes.
So when you're actually using a NMOS bias circuit in whatever you're prototyping, would there be a load connected to RG2 and RS?
Actually,
Where would the load be connected?
the load would be right here. That would be RL, and then your input would be right here. So this would be in, and this would be out. And as you'll see next week, that there are ways to isolate the in and the out. Usually you put a capacitor between the input and the gate, and you put a capacitor between VDS and output to take the DC away. But you don't necessarily have to, but you should if you're really going to use it.
So right there, right where the 0 amps is, that's where you put a cap?
You put it like here, and then you would put one here. And that would kind of isolate the output from the input. So, we'll do more of that next week when we talk about AC circuits. So this is one type of circuit, and I'm going to go through and do a PMOS circuit just to show you that they do exist. And they look very similar to the NMOS circuit. The difference is, remember that, let's see, make sure, I did this right. The source is up here and the drain is down there. And there is no source resistor. There doesn't have to be. So there is no source resistor for that. It's not there. There is one on this thing I'm looking at, but I think that was a mistake, and I fixed that. So we have the similar parameters, and we can find, this is actually a design problem, and we want to know what these values, the 3 resistor values, will be. We can find RD really easily because we know the voltage and we know the current, so that is not going to be a problem at all. And we just use Ohm's law and we find 6 kiloohms for RD. So that's great, that's easy. Now it gets more complicated because we need to figure out what value we need at the voltage divider in order to figure out what those resistor values should be. So we need to know the source to gate voltage. Since this is a PMOS, we do it backwards. So we need to know the source to gate voltage, and that's going to, again, involve algebra mostly. So we know that the source voltage is 5 because it's connected directly to 5 volts. We know that the drain voltage is 3, so the source to drain voltage would be 2. We need to find the source to gate voltage and the gate voltage. So we can actually come up with an equation that describes the source to gate voltage, which is just 5 minus whatever the gate voltage is. And in order to start, and this is always where it's hard to know where to start, the first thing we need to find is the overdrive voltage because that has within it the source to gate voltage, and we know the threshold voltage. So we need to find that first. And oftentimes with these types of problems, that's what you'll need to find. So we use the ID equation, and remember we've used it several times to solve for VOV. We've taken the ID equation and turned it around, and we've found that the overdrive voltage, and we only care about the magnitude, obviously because we're taking a square root, so we're not going to worry about the negative on it. We just use the magnitude. And we have the square root of ID times 2L over K prime P, and there is a typo up here, because this should be a P, not an N. But anyway, we know that value, and then we just plug in the numbers, and we get the square root of 0.05 milli times 2 over 1 milli, and we take the square root, and we get 1, which is a wonderfully exciting and easy number to work with. So this means the overdrive voltage is 1. So the source to gate voltage is going to be the overdrive magnitude plus the threshold magnitude. So the threshold voltage was given as -1, but we used the magnitude for that, and we add the two together and we get 2 volts for the source to gate voltage. And then, now that we know it's 2 volts, we can just take 5 minus 2 and get the voltage at the gate being 3. So yes.
Another way that, I mean, maybe this is just conceptually wrong, but if you know that VD is 3,
Yes.
so the voltage drop over RD is 3,
Yes.
and since it's in parallel with RG2,
It's not.
Oh, it's not?
No.
It just happened to be that the voltages are.
Parallel resistors are not resistors that look like that. Parallel resistors have the same voltage across them. And
It just
so
happens to have the same voltage
it,
across them?
it just happens to have the same
Okay.
voltage across it. It won't always. It just happens to be that way. And oftentimes it's not. So yeah, you could, yeah, don't make that assumption, because that's a dangerous pitfall to fall into. So now that we know what VG is, we have to figure out RG2 and RG1. And there are absolutely no parameters given for that. So basically we just have to make up a value for one and then solve for the other one, because there's no particular criteria. The only thing that is important is gate voltage, or gate resistors generally have to be in the tens of mega ohms. That's generally what happens. So we just decided, because I looked at that and went, okay, I've got 5 volts and I've got 3 volts, and so a really easy value for RG2 to be would be 3 mega ohms, because I really already know mentally what RG1 is going to be. But that was an easy value to choose, and then we can just solve for RG1, and we get 2 mega ohms, which you knew was going to happen anyway. And that's basically how you would solve that particular circuit. There are other types of bias circuits that are in existence, and that will be part of the participation problem on Friday. One of them will be a voltage divider, and then the other 2 will be different than what we've covered, but not particularly complicated. Then next week we will talk about how to actually make amplifiers out of this bias circuit, and what happens to the DC circuit once we're looking at the amplifier. Actually, the whole circuit goes away, and we just take a couple parameters from it, and we use that in a model, and we make a completely different looking model, which looks similar to the model we covered when we did large signal analysis, and we did a participation problem with that model thing. It's sort of similar to that.